Waves. Waves and particles. Particle and a wave are the two great concepts in classical physics, in the sense that we seem able to associate almost every branch of the subject with one or the other. The two concepts are quite different. The word particle suggests a tiny concentrate of matter capable of transmitting energy. The word wave suggests just the opposite, namely a broad distribution of energy filling the space through which it passes. The job at hand is to put aside particles for a while and to learn something about waves. Types of waves. Waves are of three main types. 1. Mechanical waves. All these waves have certain central features. They are governed by Newton's law, and they can exist only within a material medium, such as water, air, and rock. 2. Electromagnetic waves. These waves are less familiar, but I use them constantly. Common examples include visible and ultraviolet light, radio and television waves, microwaves, X-rays, and radar rays. These waves require no material medium to exist. Light waves from stars, for example, travel through the vacuum of space to reach us. All electromagnetic waves travel through a vacuum at the same speed c. c equals 299,792,458 meters per square. They are governed by Maxwell equations. 3. Matter waves. Although these waves are commonly used in modern technology, their types is probably very unfamiliar to you. Electrons, protons, and other fundamental particles, and even atoms and molecules travel as waves, because we commonly think of these things as constituting matter. These waves are called matter waves. They are governed by quantum physics. Much of what we discuss in this chapter applies to waves of all kinds. However, for specific examples, we shall refer to mechanical waves. Transverse and longitudinal waves. Look at this picture. A guy is operating with hand up and down in y direction, and we see a wave passing through to the positive x direction. The displacement of every such oscillating string elements, y, is perpendicular to the direction of the travel of the wave, such as in this figure. Okay. This motion is said to be transverse, and the wave is said to be a transverse wave. Now look at this is the element vibration along y direction, which is perpendicular to the direction of the wave transmit. Look at this one. This is sun. The guys pull force back and forth. Okay, we see the sun transmit in the air, and the molecule of air vibrate along the direction of the V of the air wave. The vibration of the element of the air, the dot, okay, are parallel to the direction of the propagation. The motion is said to be longitudinal, and the wave is said to be a longitudinal wave. Both a transverse wave and a longitudinal wave are said to be traveling waves because the wave travels from one point to other, as from one end of the string to other end, or from one end of a pipe to the other end. Know that it is the wave that moves between the 2 points, and not the material, string or air, through which the wave moves. Wavelength and frequency. For a sinusoidal wave, like that in figure B, okay, traveling towards increasing value of x, the transverse displacement y of a string element at the position x at time t is given by yxt equals ym sine kx minus omega t. Here, ym is the amplitude of the wave. That's the maximum displacement. The substring m stands for maximum because the amplitude is the magnitude of the maximum displacement of the spring element in either direction, parallel to y direction. Now, this is the magnitude. Okay. Hence, ym is always positive quantity. Okay, that's definition. Okay. This is y at x and t. We call it displacement at time t at location x of the element of medium. Ym, as we see, the maximum displacement is always positive. We call it amplitude. Okay. Sine, you have an angle. We call it, this sine we call it phase. And k, we call it angular wave number. X is the position. T is time. And omega we call it angular frequency. These kx minus omega t sine we call the phase. The quantity kx minus omega t is called the phase of a wave. Y at xt equals ym sine kx minus omega t. This is a propagation wave. Okay. This is amplitude ym. This is a phase. If we look at this, this is a wave propagation along the x direction. At the one instant, it's this way. We look at this point. Okay. But later, we find it goes to x. And this is a repeat. We call lambda. We'll talk about it later. Okay. It can repeat, repeat, and repeat. Okay, this is the shortest repeat unit. Another time it's go this way. Another time it's go. So we see the wave move towards the positive x direction. And look at this. Okay, at this point x. At this moment, it's this amplitude displacement maximum, and at this moment it go this one. At this moment it go down. It gets so this point is going up and go down when the wave move. Let's look at another one. Another one at the beginning is 0, and then it go down, and then it go back and go up and go down. So it moves up and down, up and down, and we will see that the maximum displacement for those points are the same. This is the ym. You may wonder why of infinity variable of waveforms that are available, we pick up the sinusoidal wave for detailed study. This is in fact a wise choice because all waves formed, including the paths, can be constructed by adding sinusoidal waves of carefully select amplitudes and the value of omega. So understanding sinusoidal wave is thus the key to understanding the waves of any shape. Now, this is y at t, ym sine of t. So we see y is function of x or t. Okay, we can write this one. So we study this way. We have two ways because you have x and t, two variables. So we take x as constant. So we standing there, watch the motion of the element of medium. Also, we can take t is constant. And we look at different x, okay, so that we can watch the waveform. At different point, it has different displacement. Wavelength and angular wave number. What is the wavelength? Look at this wavelength. This is x, this is t. So we look at it at the same t. Suppose the t equal to 0. T can be any one number, okay? Suppose t equal to 0, this kind of a wave. We look at this wavelength. Wavelength lambda of the wave is the distance along the direction of the wave, x, between repetitions of the wave shape. They repeat again and again. This is the shortest repetition unit. Or we take 2 lambda, it repeats. 3 lambda, it repeats. We take the shortest lambda, okay? So, what does this mean in mathematics? Mathematics is y at the same time, x1, this one, y, equal to y, x plus number. X plus number, this is x1 plus number here, repeated. This y is the same as this y. So this is mathematics. This is mathematics. We look at this. Y at xt equal to ym sine t. So we take t equal to 0. T can take any point. At any point, x1, the yx1 is for this one. Ym sine kxx1. This is a t. And of t, x1 plus lambda equal to ym for this one, at kx1 plus lambda. This is a t, 0. And we, by definition, the lambda, yx1 equal to yx1 plus lambda. And so this one equal to this one. Okay? We write ym sine x1 equal to ym sine kx1. We compare these two. Ym cancel out. So the phase inside must be same or a little bit different. What are different? Okay, kx equal to kx1 plus k lambda. So k lambda by trigonometry, k lambda must be equal to 2 pi or 2 pi, 3 pi, 2 pi plus m. Since we take the shortest repetition, so we take m equal to 1. K lambda equal to 2 pi. Or in this case, we will find the k we call the angular wave number. Okay? Because in the angular sign, this is the angular wave number, k. In metric system, this is called radial, this is radial, over meter, lambda is meter. K equal to 2 pi over lambda, or lambda equal to 2 pi over k. We know lambda, we know k, we know k, we know lambda. Period, angular frequency, and the frequency. At any position x, we fix that. We watch it, the vibration of the element of medium, okay? And for example, we take x equal to 0. X can any position. And we watch the vibration. This is time t, not xt. And the same x, so its vibration, we record and plot it. What is the period? Period, we define the period of oscillation t of a wave to be the time interval between repetitions of the motion of an oscillation string element. I would say that the shortest repetition, okay? So, what does this mean? Mathematics, y at x is 0 time t, t1, this is a y at x equal to t1, equal to y, x is the same 0, t plus t, this is a t plus t, this is a period, the y are the same. We can take any x, that means different point, we get a definition. The same reason, you see, yxt equals ym sine kx minus omega t. And we take x equal to 0 at time t, y t1 equal to, this is a t1, this is 0 minus omega t. And y0 t plus period t, we put this one, t plus period t. This is 0 minus t. Since definition of the period, y0 t1 equal to y0 t1 plus t. This is minimal representation, okay? So we put this one inside. So we get this one is ym sine minus omega t equal to this one, ym sine minus omega t. We compare this equation, we find, okay, minus omega t1, minus omega t1. So minus omega period must be an integral number of 2 pi. It can be 2 pi, 3 pi, n 2 pi. Since we take the minimum, so we'll take n equal to 1. So omega t equal to 2 pi. Then we know the period equal to 2 pi of omega, or omega equal to 2 pi over t. The omega is called the angular frequency. This is the frequency in the angle, the sine angle, angular frequency of the wave. Its metric system unit is called radius over time second. Okay. T equal to 2 pi over n, or omega equal to 2 pi over t. The frequency f of the wave is defined as 1 over t. Okay, so once we know omega t or frequency f, one of them, we can find another 2. So omega is called angular frequency. How do I remember? This is frequency. 2 pi is the angle. So the angle frequency is omega. Speed of an travel wave. We look at this wave move, okay, from the beginning, the green line, to this brown line, okay, with velocity v. So what we do, we should, at that time interval delta t, it moves delta x, and its velocity is delta x over delta t, or dx dt. How do we find this one? The wave is traveling in the direction of increasing x to the right of the figure. The entire wave pattern move a distance delta x in that direction during the interval delta t. The ratio delta x over delta t, or in differentiate limit dx dt, is the wave speed v. How can we find v? We can take a different reference point. For example, from this point to this point, from this point to this point, the delta x are the same in the same period, right? So we look at this. How can we find the velocity? Okay, now this is the wave. Okay, we look at this too. Is we find the particular part of the wave pattern. The phase, the same phase, the same y. So we take the phase is constant, okay? Phase is constant. Different phase, this is the one phase, okay? No matter what constant it is. For example, we can take this phase, we can take this phase, different constant. So at the same time t, it moves the same distance, okay? The issue in physics, in math, we take this phase, it's constant. What the difference, the phase constant means x and t combination different, okay? At time t1, x is here. At t plus delta t, x is here. Anyway, this is constant. So in this case, we can find dx dt. We do the derivative on both sides. This is k dx dt minus omega equal is constant. So dx dt equal to omega over k. Okay? When we know omega t is 2 pi, k lambda 2 pi, we put this one, we get equal to lambda over t. And then 1 over t is f. Okay? So we have the velocity of the propagation wave, v, equal to lambda f, equal to omega over t, equal to lambda over t. One of them, omega t or f, you can find the other two. Now, how do you remember this one? Let me remember this one. What is velocity? By definition, velocity is the distance traveled in unit time, called velocity, right? So dx dt. Yeah. Okay. For example, 1 second. 1 second, how many distance it travel? We say, in 1 second, it repeats 3 times. That's the definition of frequency. And each time it moves a wavelength lambda. So V equal to F lambda. This is the way I remember that one. Okay. The wave speed is the distance traveled in 1 second. And in 1 second, the wave repeat F time. Repeat F time. And each time you travel a wavelength. So V equal to lambda F. In 1 second, the wave oscillates F frequency cycle. Each cycle has wavelength lambda long. This is how do you remember this velocity of the propaganda longitudinal wave?
On this wave machine, long rods are attached to a square wire spine at regular intervals. If we tip the first rod, a torsion wave travels down the spine. This wave machine is identical to the first, except that the rods are shorter. A wave travels faster on this machine than on the other one.
Okay, yxt equal to ym is kx minus omega t. Wave travel along positive x direction because this is minus, we will prove it. Okay. We have another one. Another one is positive. This is negative. This is the wave travel along negative x-axis. Why? From here, constant, okay? We do the derivative on both sides. We get a k dx equal to, let's see, we get a k dx plus omega 0. So v equal to minus omega over k, equal to minus lambda over t, equal to minus f lambda. It is propagated along negative x-axis. Traveling waves must be informed xt is kx plus minus omega t. This is a linear relationship combination, okay? So this is a xt is a linear combination. It is possible a travel wave. And this is not, because this is square. It's not a linear relationship, okay? Sample. A wave traveling along a string. It's described by this one. We have this one, ym. This is the k, omega, in which the number constants are in metric system. This is meter, this is radian per meter, and this radian per second. Okay? What is the amplitude of this wave? This is one. Okay? So y equal to 0.00323. This is a meter unit. Okay, or equivalent to 3.27 millimeter. Question B, what are the wavelength period and frequency of this wave? This wave, we know K, 72.1. We know K lambda is 2 pi. So we know K, we know omega. Okay, what is the lambda? Lambda is K lambda equal to 2 pi. So lambda equal to 2 pi over k, we get this one. Okay? Yeah. Frequency equal to 1 over t. A period, okay, what is period? Period equal to 2 pi over omega, right? So we put this omega in, we have this omega, we get a frequency. What is the period of this, or what is the velocity of this wave? The velocity, make this one derivative with the time t. We get velocity equal to omega over k. We know omega, we know k. We get a 3.77 centimeter per second. Okay. What is the displacement x? Displacement y at x 22.5 centimeter and t 18.9 centimeter. Very simple. We put xt inside, we get y. We see in this formula, okay, we get a lot of information, okay. The amplitude, the lambda, the k, angular wave number, and the omega, and from omega we get a period, from k we get a lambda, okay. Remember, k x 2 pi, omega t 2 pi. Sample. In the above sample, we show that at t 18.9 seconds, the transverse displacement y of the element of the string at x 0.225 meter due to the wave is 1.92 meter. Okay? Question A. What is u, the transverse velocity of the same element of the string at that time? Remember, this is the speed of the element of the spring. So it's along the y direction, okay? On direction. Do not confuse it with v. There's different v. V is the wave velocity, while u is the velocity of the element of the string. Okay? So we know this y. This is the displacement of the element of the string. What is velocity? dy dt, or round y around t. Okay? We do this one with respect to time t. We get a minus, we get omega out. So we get du t equal to, we take this minus out, and sine becomes cosine and y. Okay? So we put the number in sine. We get omega, we get the ym, we get a k, we get the x, we get the omega, we get a t. That's elementary mathematics. I'm going to do it. Question B. What is the transverse acceleration A of the same element at the time t? This is acceleration of the element of the string, not the wave. Okay? This wave is traveling uniform speed. Okay? So this A is second derivative round x round t. Okay? Is round u round t. We could do this one around t again. So cosine becomes minus sine. You have another minus, so you get a 3 minus omega sine. And originally you have minus, so you get a minus omega squared. Okay? That's squared. Okay. Finally, A is minus omega squared y. You look at this one, what do you find? You find A proportional to its displacement. So this is a simple harmonic motion, okay, with frequency omega.